Alright, this last video for Unit 2 is going to focus on enthalpy calculations, specifically Hess's law, and calculations involving enthalpies of formation. Hess's law is basically just algebra, and it's what we did in our thermodynamics lab, that if you have a reaction and you know the enthalpy of two reactions that would combine together to make that reaction, you actually can determine what the enthalpy is for that reaction. You can combine them in a variety of ways. You can combine them by reversing the reaction. It would go from being endothermic to exothermic, so the enthalpy sign would change. You can also change the enthalpies of the reactions, since enthalpy is an extensive property, because that's basically your Q value. It's determined based on the amounts of reactants and products you have. So if you need to increase them by multiplying them by a common factor, you would also multiply delta H by that factor. I have here, it could be an integer. It could also be a fraction. It really doesn't matter. Because if you had to reduce it, say divide by 4, if you divide the delta H by 4, you would still have it in the right proportions. And so these next two examples are going to do that, show you how that works. So what we have here are three combustion reactions. We have ethine undergoing combustion, we have carbon undergoing combustion, and we have hydrogen undergoing combustion. Combustion is an exothermic reaction, and we see that in the delta H values that are provided. And we're going to calculate delta H for the reaction in which ethine is synthesized from the elements carbon and hydrogen. So we need to find a way to get these three equations that were given to be set up so that we are left with the equation we're wanting to form. We want carbon to be a reactant, and carbon is in our second equation, but we want there to be two carbons in our equation, so we would need to take that equation and double it to account for two carbons, and when we do that, we would double our delta H by 2 as well. So if I rewrote that, the 2 would be multiplied through to the whole reaction, so it would be 2 carbons, 2 oxygens, make 2 CO2 molecules, and the new delta H value would be negative 788 kilojoules. Hydrogen is our other reactant. We have one of them in the equation we're trying to make, and we have one hydrogen up here in our equation. So when we write that one down, we see that its delta H value does not change. It is negative 286. Ethine, which we're trying to make, C2H2, is a reactant in our first equation, but we need it to be a product in our final equation. So we're going to need to reverse this reaction, and so we're going to make combustion occur, or no longer occur. We're going to take the carbon dioxide and water and use them to make a hydrocarbon and oxygen. That is similar to photosynthesis, and it will require an input of energy. So our reaction will now require 1300 kilojoules of energy in order for it to occur. Now you can see the changes in blue. And if we combine these three reactions together, basically treating the arrows like equal signs, we will see that we had 4.5 oxygens here, 2.5 oxygens here, and 5 halves is the same as 2.5. So those would cancel out since they're on opposite sides of the arrows. We have 2.5 molecules of oxygen as reactants, and we have 2.5 molecules of oxygen as a product. We also see the same thing for H2O. We made one H2O molecule in the second equation, but we consumed it in the third. And then we also made and used 2 CO2 molecules. And that leaves me with 2 carbons and a hydrogen on the reactant side, forms C2H2 on the product side. So once I've combined that reaction together, and I add these three enthalpy values together, I get that the enthalpy of this reaction in order to form ethine, it would require an input of 226 kilojoules, as it is an endothermic change. So one more. We're going to see how hydroquinone can undergo oxidation in the presence of hydrogen peroxide, and that what it makes as a result, quinone and water. So this is the hydroquinone, this is the hydrogen peroxide, there's our quinone, and there's our water. So we need to find a way to get it so that the aqueous form of hydroquinone is on the reactant side, and that the quinone is on the product side, along with the hydrogen peroxide and water. So if we take a look at our first equation, we see that hydroquinone can form quinone by giving up a hydrogen molecule. So So that takes care of one of our reactants and one of our products. We now want to find hydrogen peroxide as a reactant. We see hydrogen peroxide as a product in our second equation. So if we reverse that reaction, we would also have it as a reactant. When we reverse it, remember that the sign of our reaction changes from being exothermic to endothermic. So we see the red plus to indicate that that has happened. We've already taken care of the quinone, and now we need to have water as a liquid. Well, we have water here as a liquid, and we need 2 water molecules, so we would need to double that reaction. In the process, we would double the enthalpy released, so it would go from negative 43.8 to negative 43.8 times 2. I think that's going to be around 87.6, but don't hold me to it. Now, if we look here, we see that we have our quinone, we have our hydroquinone, we have 2 hydrogen molecules, we have an oxygen molecule, we have water as a gas, and we have water as a liquid. We don't want water as a gas in our equation. We also don't want hydrogen and oxygen in our equation. And we haven't used this third equation yet. Hopefully you're seeing now why we would need that equation, because it's going to help us to remove the products and reactants that we do not need in this reaction. But we need to have 2 water molecules as a gas. So since this equation only has 1, we would double everything. So we would make the hydrogen go to 2, the oxygen would go to 1, and we would form 2 water molecules in the gaseous form, and we would double the enthalpy value for that as well. Once we account for that, if we cancel everything out that is on opposite sides of the equation, we have 2 hydrogen molecules as products and 2 hydrogen molecules that were consumed as reactants. We have 1 oxygen that was consumed as a reactant and then released as a product. And we have 2 water molecules in the vapor form that were used as a reactant and then formed again as a product. So now we see we have the 2 reactants that we wanted to get, along with the 2 products that we were trying to form. And so when we take these 4 delta H values after doubling these 2 and changing the sign of the second one and add them together, we see that this process of oxidation actually releases energy. It releases negative 202.6 kilojoules of energy. So that's one part of this section. Alright, so this second section of the video is going to focus on standard enthalpies of formation. If you do not have this chart out, you're going to want to get it. A lot of the notes that I'm going to give you now are the examples. They're going to refer to Appendix L. This was when I used to use the book. What we're going to be using is a chart I gave you in class. It looks a lot like this. The standard thermodynamic quantities for selected substances at 25 degrees Celsius, which is your standard temperature for these thermodynamic values, which is why they got to use that degree sign. So you're going to want to have this out while we're going through the second half of this PowerPoint. These enthalpy values are basically telling us how much energy would need to be absorbed or released to form that substance under conditions that you would not normally find it as. It could be as a compound, it could be as a gas, as an element when it's normally found as a liquid. It could be in solution, AQ. But basically what it would take to form that substance from the elements that are normally found in standard conditions. To find the enthalpy change for a reaction, those are the enthalpy values we were just seeing with Hess's law that were written at the end of each equation. We take the difference between the energy that is being released or absorbed by the products and their relative stoichiometric amounts, and we subtract away from it the energy released or absorbed by the reactants, because that's what would be used in the reaction, times their stoichiometric ratios. If you have an element under normal conditions, such as bromine is a liquid at 25 degrees Celsius and 1 atmosphere pressure, aluminum is a solid at 25 degrees Celsius and 1 atmosphere, neon would be a gas. They don't require any energy, and they also don't release any energy to be formed, because that's how they're normally seen, and so their enthalpies of formation would be 0. So it says use the values of delta H and of F and I know yours says Appendix L. I'm referring to that table we just showed you to calculate delta H for the following reaction. Sorry about the plural. Ethanol is going to be combusted in the presence of oxygen to make 2 CO2s and 3 H2Os as a gas. So we're going to go over to that chart. I'm going to show you how I got these 4 values based off of that chart. I won't refer to the chart after this, but I just want to make sure that you're comfortable with where these values are coming from. So the chart is arranged by elements. Sometimes it's under the element you would think, sometimes it's under a different one. So if you don't find it under the element you're looking for, keep looking. They will be here. We wanted to start with ethanol as a liquid. Ethanol as a liquid has a delta H value of negative 277.6. The delta H values are always in the first column, so that helps some. We're going to scroll down to oxygen. Oxygen is a gas, and that's how you would normally expect to find oxygen at 25 degrees Celsius. So we're going to see here that oxygen does not have a delta H value, of that value, and that's because it's when it's formed, it doesn't require any energy to make oxygen stay as a gas at 25 degrees Celsius. We're going to go back up now and take a look at CO2. We said carbon dioxide was a gas. We have carbon monoxide as a gas, we have carbon dioxide as a gas, and we have carbon dioxide as an aqueous solution. We want to make sure we grab the right one, the negative 393.5. And now we're going to go find H2O. H2O is actually not under hydrogen, it is under oxygen. So don't be surprised again if you don't find it where you think it would be. Just keep going through your elements. We have water as a liquid, water as a gas, hydrogen peroxide as a liquid, hydrogen peroxide as a gas. We want the second one, the H2O as a gas, negative 241.8. So just take your time to make sure you get the right values, because otherwise that could cause some complications with your calculations. So again, the delta H for this reaction will be the difference between the enthalpies of formation of the products minus the enthalpy of formations of your reactants. Our products, we have 2 CO2 molecules, and so if we were dealing with moles, we would have 2 moles of carbon dioxide, and we're going to release negative 393.5 kilojoules for every mole of CO2 that's formed. We would add that to 3 moles of steam that are generated, 3 times negative 241.8. So this is the sum of the product's energies. We're going to subtract away from it the sum of the reactant's energies. We only have 1 ethanol molecule at 277.6 kilojoules per mole, and we have no oxygen values. You can write the 3 times 0, or you can just keep going and stop here. I understand if you don't want to include the 0. I just wanted you to see where it was going from. So the moles cancel, and when we multiply and add, so you'd have 2 times the negative 393.5, 3 times the negative 241.8, and we would subtract away 1 times the negative 277.6. The 2 negatives make this term positive, and when I did my math, I got negative 1234.8 kilojoules of energy was released in this reaction. We can't say kilojoules per mole because the stoichiometric ratios are not the same for the reactants or the products. Okay. So here we're going to look at nitroglycerin. This one looks like it's going to be more complex. We're showing that nitroglycerin, when it's decomposed, it produces nitrogen, oxygen, carbon dioxide gas, along with H2O gas. Remember that the elements, if they are in standard conditions with both nitrogen and oxygen are, they have delta H's of formation of 0. We know what the glycerin delta H value is, and we saw what CO2 and H2O were on the previous slide. So again, nitrogen is at 0 because it's an element in its standard state. Same thing for oxygen. You could do 1/2, 3.5, they mean the same thing. We would take 6 carbon dioxides at negative 393.5 and 5 vapor molecules at negative 241.8. And we're going to subtract away from it. This is how I would give you a value if it's not one on the chart. Nitroglycerin releases 364 kilojoules of energy per mole of nitroglycerin. The 2 negatives make that term positive. And so when I do my math through, 0, 0, 6 times the negative 393.5, 5 times the negative 241.8, and then the 2 negatives would be adding 2 to times 364. The moles go away, and I got a delta H value for this particular reaction of negative 2,842 kilojoules. Our last example It's going to go about things a little bit differently. This time I'm giving you what the combustion enthalpy is, so that's the reaction delta H. And we're going to use that information to find what the delta H of formation is for ethene, C2H4. So in order to do that, we need to write a balanced equation showing ethene going through, I'm not sure why I said ethane, this is ethene, going through combustion. So 2 carbons, 2 CO2 molecules, 4 H's, 4 hydrogens with 2 H2O vapor molecules. That gives me 4 plus 2, 6 oxygens, so 3 O2 molecules. Again, I know that oxygen will be 0. Carbon dioxide I've already seen, along with H2O. This is the one I'm trying to find. And I know that together, when those are combined, they give me a total value of negative 1411.1. I have that this value would be equal to the sum of my products times their stoichiometric ratios, 2 times the negative 393.5, and then 2 times the negative 241.8. I'm trying to find out what ethene is, and I have 1 mole of it, so that's why I have 1 mole times X, and then the 3 oxygen molecules would set me to 0. This time I'm going to show you the math through because I want you to see how we get X. Negative 1411.1 kilojoules would equal 2 times the negative 393.5, negative 787.0 kilojoules, plus 2 times the negative 241.8, negative 43.6 kilojoules, minus 1 mole of X. So when I combine the constants together, I get that they should equal approximately 140.5 kilojoules. So X is 140.5 kilojoules per mole. And that should get you through the last section for Unit 2, Part 3.